Okay, let's start. Welcome everyone to the ITMP seminar. And today we are happy to have Dmitry Chicherin, who will speak about Null Wilson loop with Lagrangian insertion in n equals 4 super Young-Mills theory. So please go ahead.
Okay, thank you. This talk will be about certain observable in n equals 4 super Young-Mills theory. But as a motivation, I would like to start with some real physics. As we will see, this observable, which we are going to discuss, is closely related to some calculations which are needed for doing collider physics. So right now we are in the era of improving experimental precision at the hadron colliders, and these experiments are designed to test the accuracy of the standard model and to find possible deviations. And in order to do it, we need predictions from the theory, certain theoretical calculations. And the level of experiment is such that from the theory, we demand very high theoretical predictions nowadays. More explicitly, we need so-called next to leading order prediction in QCD. So in QCD, at high energies, we work in the weak coupling regime. And we find we need this approximation next to the node, which roughly correspond to loop expansion in quantum field theory. Also, among many different processes which we would need to calculate for colliders, I'm particularly great interested in 2 to 3 processes. So not only we need a relatively high loop order for collider calculations, but also we need more complicated processes with production of many particles. And what is measured in colliders, these are cross sections and event shapes. And to theoretically calculate these objects, we need several ingredients. In particular, we need to know parton scattering amplitude in QCD, and more precisely, their finite parts of QCD amplitudes where all infrared divergences are factored out. And huge progress in calculation of QCD amplitudes recently became possible due to experience which we gained in previous years working with amplitudes, scattering amplitudes in maximally supersymmetric Young-Mills theory. So this supersymmetric theory is an excellent theoretical laboratory where we can develop new calculation techniques. So in particular, these different techniques to construct tree-level amplitude, to construct integrands of loop-level amplitude, as well methods for doing loop integration. So they initially appeared in the context of n equals 4 super Young-Mills theory, and later they were successfully carried over to calculations of QCD amplitudes. But what is interesting that amplitudes in n equals 4 super Young-Mills theory are much simpler than usually are QCD amplitudes. So what I mean by this? Let's just count number of independent variables on which amplitudes depend. Let's consider finite part of amplitude. In QCD, it depends on 3 and minus 11 variables. And in Conformal super Young-Mills theory, well, it depends only 3 and minus 15 variables. So, well, it's due to symmetries, hidden symmetries of n equals 4 super Young-Mills theory, which severely restricts the functional space of the amplitude. So let's substitute here numbers for number of particles. In the case of four particles in QCD amplitudes, finite part of QCD amplitudes are functions of one variable. Whereas in N=4, amplitude is completely fixed by symmetries. Similar story in the 5-particle case. So 5-particle QCD amplitude depends on 4 independent variables, its finite part, and in N=4, the terminal's amplitude is completely fixed by symmetries. And only starting from 6 point, amplitudes in N=4 superkernels become non-trivial. So they depend on they are functions of 3 independent variables and so on. And as I mentioned previously, for collider physics, for QCD calculations, it's of great interest to do calculations of 4-particle and 5-particle amplitudes. But in N=4, these amplitudes are well known or trivial, fixed by symmetries. So, as we can see, a huge amount of symmetries of N=4 severely restricts amplitude. So, we can say that it's good, but it's not good if we want to learn something new about 4 and 5-particle amplitudes in a QCD. So, we would like to ask a question. Can we find an observable in N=4 superkernel theory which resembles more closely finite parts of QCD amplitudes, such an observable which is already non-trivial in the 4-particle case? Well, as we will see, yes, such an observable exists, and it's a ratio of 2 correlation functions. In the denominator, it's a vacuum expectation value of polygonal Wilson loop, and in the numerator, the same polygonal Wilson loop and Lagrangian. So correlation function of Lagrangian of N=4 superkernels and Wilson loop. Lagrangian is denoted here by cross. Well, as we'll see, this observable is finite in superkernel theory, so it can be defined exactly in 4 space-time dimensions. And we'll see that it's very similar to massless scattering amplitudes in QCD. Moreover, it also displays very nice features of amplitudes in N=4 superkernel theory, such as it has hidden symmetries, which resemble a lot Youngian symmetry. It also related to Grassmannian representation of amplitudes, and there is a very interesting story related to amplitude heteron geometry and positivity. Well, to motivate this definition for this ratio of the correlation functions and explain why it is related to amplitudes, I would like to recall something known about duality between Null Wilson loop and scattering amplitudes in the planar limit of N=4 superkernel theory. So on the one hand side, we have a polygonal Wilson loop such that contour is light-like, namely distances between adjacent cusps are light-like. That is, for example, x4 minus x5 squared equals to 0. So, taking differences of adjacent coordinates, we can call them new variables p this way, and these p are light-like. And using these p, we can call them momenta and consider scattering amplitude. Where p are momenta of scattered particles. And in N=4, the simplest non-trivial amplitude is the so-called MHV amplitude, which has 2 negative helicity particles, and all our particles have positive helicity. Well, and it happens that these 2 objects coincide, and this duality equivalence of the objects, it holds as well as on the level of regularized quantities, as well as on the level of their finite integrants. I'm going to briefly recall definitions of these 2 objects, of a Wilson loop and of a scattering amplitude. So let's start with Null Wilson loop. So we have n points in Minkowski space. They are ordered, and the distances between two neighboring points are light-like. So we define light-like polygon. We define Wilson loop along this polygonal contour. So this is bosonic Wilson loop. It means that a gauge field is lives on these edges of this polygon, and so we take path ordered exponent along this contour. We traced it to a fundamental representation of the gauge group and normalized by the rank of the gauge group color of the color group. And to calculate vacuum expectations value of this Wilson loop, we just stretch propagators between edges of this contour, and also these are gluons, and they can interact in a Abelian way. So we can calculate with object in perturbative expansion in this coupling, in the weak coupling. A nice feature of this object is that its divergences has a very nice pattern. So first of all, it's divergent, and the divergences originate from the region of short distances, from the cusps. So when we integrate in this vicinity of cusps, we find divergences, and to regularize them, we use dimensional regularization. Well, it happens that this divergences has a very nice pattern. If we take logarithm of the Wilson loop, then this object has very mild divergences. Its divergences manifest themselves as a second order poles. Well, obviously, if we take exponent of this object of logarithm, we get Wilson loop, and we find that in the L-order approximation, we find that poles are of order 2L. So logarithm of Wilson loop has divergences which are milder than divergences of a Wilson loop itself. And,
can I ask a question?
Yeah, sure.
You draw the diagrams which involve on the gluons, but there are of course other diagrams.
Yes, of course, yes.
But the question is, for example, for some Wilson loops, we know some classes of diagrams do not contribute. So what is known for null cusps? Generically, all possible vertices will contribute, or for example, so there is no any statement that there may be some cancellations of some particular diagrams.
Okay, so here I just wanted to say that, first of all, a beta function of n equal 4 is 0, so all divergences, these are divergences coming from short distances, and they originate in this region of cusp. So it's a main message, and here this diagram is just a typical diagram. Of course, there are other type of diagrams which involve other interactions of n equal 4. So I don't know if I answered the question or not.
Yeah, okay. I take it off. Yeah.
Okay, so what we need, what we will use in the following, that this object is divergent, it's integralization, and the logarithm of this object and divergence is exponentiate. So logarithm of this object has a very nice structure of divergences. Then if there were no divergences, then this object would be invariant under conformal transformation. We call them dual conformal transformation in the following, because we are going also to discuss amplitude, and amplitude has another conformal symmetry. So this symmetry is anomalous because of divergences, but anomaly is understood, and and known. So symmetries of this object also understood. Okay, a second object that we'll need are scattering amplitudes. So let me briefly review scattering in the planar gauge theory. So we have n particles and states. Each state, we assign to each state its mass, its slate-like momenta, its helicity, and color index. So we consider scattering of gluons, and among gluon amplitudes, the simplest is so-called MHV amplitude, which has two gluons of negative helicity -1 and other gluons of positive helicity +1. So we work in the planar limit at the weak coupling, and this amplitude has the following color decomposition. So all information about color can be factored out in the form of trace of color matrices, and what remains here is a so-called a partial amplitude, which doesn't depend on the color. So color appear here only in this Hoof coupling in the form of it comes in the as a Hoof coupling here. So it's a non-trivial function of particles momenta. And in the following, we work in the planar approximation. So we drop away all other contributions which contain products of several color traces. So we keep only single trace. Okay, so this amplitude has a perturbative expansion in weak coupling, and loop corrections contain divergences. These divergences are soft collinear divergences or infrared divergences. So such that at high loop order we have we find poles of order 2L. Lagrangian of a theory is invariant under conformal transformations, but these divergences they spoil with conformal symmetry, and only a three-level amplitude, three-level part of the amplitude is invariant under conformal transformations. Similar to Wilson loop. Divergences, infrared divergences of the amplitude, they exponentiate and can be factored out. So if we take logarithm of the amplitude, we can write it in this way, where all poles appear as logarithm of infrared renormalization factor, and here we have only 1/epsilon² poles. Plus finite part. Here it's very convenient to split out finite one loop amplitude. And then in the 4-point case and 5-point case, this is it gives a full answer. So there is no extra contribution R. So in this case, 4 and 5 particle amplitudes, so they are given by exponentiation of one loop amplitude. So this formula is, so this is exact answer for amplitude at any loop order. But starting from 6th loop, there is a non-trivial remainder, finite remainder, and it was calculated in recent years up to 7 loops, and in the 7 particle case is known up to 4 loops. It's very staggering. It's very staggering loop order. So as I mentioned previously, amplitudes in n=4, they non-trivial only starting from 6 points. In the 4-point and 5-point case, they are known at any loop order. Okay, so now let's recap this duality again. On the one hand side, we have a null polygonal Wilson loop. On the other hand side, we have a bosonic amplitude, MHV amplitude, and then there is this duality. We need to define momenta of amplitude in these various difference of coordinates of the Wilson loop, and this duality maps divergences of two objects and also finite parts of two objects. It also maps symmetries such that conformal symmetry of Wilson loop, although conformal symmetry is mapped to hidden symmetry of amplitude. So this duality is not trivial because it's duality between two divergent objects. So let's just consider duality. Let's see that this duality also holds at the level of their finite integrands. So how to define integrand of Wilson loop? So let's consider expansion of Wilson loop in the coupling. It starts with 1, and we okay, we have one loop correction, two loop correction, and so on. How to find these terms of this expansion? We will rely on this Lagrangian insertion trick, which is due to this formula. So when we differentiate Wilson loop in the coupling, we find that we can find that these derivatives is a correlation function of Wilson loop with insertion of Lagrangian, where Lagrangian is integrated out. Well, how to prove this formula? Well, we can represent Wilson loop as a path integral where we integrate out gauge fields as well as all other fields of n equal 4. So here this is the action of n equal 4, and this is Wilson loop. Okay, we can rescale the field such that dependence on the coupling comes here only as a prefactor in front of Lagrangian. So when we take derivative in the coupling, derivative hits only here. So we don't differentiate Lagrangian or Wilson loop. Coupling disappears from them. So when we differentiate in the coupling, what we do, we insert the action here on the path integral. So, and this is exactly this formula. So there is several subtleties how to choose the Lagrangian. Well, it can be done in different ways, as we'll see. A convenient way for us is to choose Lagrangian in so-called chiral on shell form. It's equivalent to the standard form of n equal 4 Supermill's Lagrangian up to total derivatives and equations of motion. So, for example, it starts with this f squared term where f is a chiral part of strength tensor. Okay, so let's apply the Lagrangian insertion formula to perturbative expansion of the Wilson loop. So we substitute in this formula this expansion and evaluate it at the lowest perturbative level. So it means that what we obtain one loop correction, and here we would like to evaluate this correlator at the lowest perturbative level, Born level. So it means that this correlator is evaluated at the lowest perturbative level is the integrand of one loop correction. This formula can be extended to higher loops such that a loop correction is given by a correlation function of Wilson loop and L Lagrangians. And this correlation function is evaluated at the lowest perturbative level. So it is L loop integrand. So integrand is a finite rational function, which is also well defined in 4 dimensions. So what about integrands of amplitude? How we define them? Well, first of all, we would like, instead of momentum, we would like to introduce dual variables axes, which come in, which appeared previously in duality between Wilson loop and amplitudes. So to each external moment, for each external moment, we introduce this dual momenta axis, and also for loop momenta, we introduce the duals, which we call here y's. Well, in the planar case, this assignment of dual momenta is unambiguous. and the integrand is well defined. So in particular, we can just take all contributing Feynman diagram in L loop amplitude, replace rewrite expression where we replace momenta by dual momenta, and the result will be unique and independent of how we choose loop momenta. Okay, but there are also another ways to do it, more efficient way how to obtain four-dimensional integrands of amplitudes. In the recent years, many different techniques have been elaborated. There are loop on-shell recurrence relations. Also, there are geometric approaches based on Grassmannian and canonical forms in positive geometries, as well as twister approaches, and also approaches which could be also more practical to bootstrap integrands using its symmetries and analyticity. So in principle, integrand can be found at any loop order, but in practice it's difficult, but still it's known at very high loop order. For example, in a five-particle integrand is known at 10 loop order. Well, now, so we have an integrand of amplitude and the integrand of Wilson loop. Well, it happens that these two objects coincide. Well, it can be seen in several different ways using twister Feynman rules. Just these two objects satisfy the same set of recurrence relations. That's why they coincide. Or it can also be seen that they are limits of a master object correlation function of composite operators. Both objects can be obtained from it. But what important for us that okay, these two functions, they coincide. So to recap, these are rational functions. Coordinates here live in coordinates in four-dimensional Minkowski space. These rational functions, they correspond to planar topologies of Feynman integrals. They have all the local poles, and they have the invariant and dual conformal transformation. Also, they have non-trivial chirality property, namely they contain the parity and parity order contribution. This chirality is, well, on the side of the Wilson loop, we can understand it from these Lagrangians. So we chose Lagrangian in a very particular way. Lagrangians are chiral, so this correlation function also has chirality properties. Okay, let's consider a simple example, one loop example. Wilson loop integrand, one loop integrand. It is given by correlation in the four cusp case. So we take four cusp Wilson loop, Lagrangian, and well, we draw all possible Feynman diagrams. So these three plus their cyclic permutations. So we evaluate all diagrams, and we find that the result is a very simple rational function. Okay, what about MHV amplitude for particle MHV amplitude? Well, if we sum up all contributing Feynman diagrams, we find that it's just a box decorated with this numerator, which doesn't depend on loop momentum. So K here is a loop momentum, P are external momentum. So this is integrand of one loop MHV amplitude. We can introduce this dual momenta. Well, and write integrand in terms of them. As we can see, these two integrands, integrand of Wilson loop and integrand of MHV amplitude, they coincide. Okay.
Sorry,
yeah.
Why is there only a single diagram below?
Well, it's a sum of many different diagrams. So I would have to draw diagrams with gluons and so on. There are also triangular diagram and so on. But if we take sum all of them, we find that the result is in this, like this one.
And is there any like kind of diagram by diagram matching? with the upper picture, or just for the total result?
No, it's well, it's total result. Also, well, probably I should mention that here it could happen that individual diagram here they are not rational, so it's only sum of diagrams has nice properties. It also could happen that individual diagrams have divergences. Well, at least at two loops, it's the case. So it's only sum. So well, the idea that okay, maybe we should forget about Feynman diagram approach, but look at the final result. So there are, well, it's just for the sake of illustration that this function can be obtained in a simple, well, in a way, naive way, just by drawing Feynman diagrams, completing Feynman diagrams. But of course, it's not the best approach to find this function.
Mm-hmm. Thank you.
Okay. So let's come back to this ratio of Wilson loop with Lagrangian insertion and just vacuum expectation value of Wilson loop. Okay, so this, as we discussed previously, there are divergences here in numerator and denominator, and they are due to cusps. But these divergences, they cancel out in this ratio. So this ratio is finite. It's a finite function. How can we interpret this ratio? What's the meaning of it? Let's take logarithm of Wilson loop and differentiate it in the coupling. Well, previously I discussed this Lagrangian insertion trick. So when we differentiate Wilson loop in the coupling, it's equivalent to inserting Lagrangian in integrating out Lagrangian. But here we differentiate logarithms. So we also get normalization by vacuum expectation value of Wilson loop. So in other words, this f integrating out x0 of this f, we obtain derivative of log of Wilson loop. And as we discussed previously, divergences of Wilson loop, they exponentiate. So taking logarithm, we find that it's just 1 over epsilon squared divergence. So what it means, this f is finite, but when we integrate this x0, we get divergence 1 over epsilon squared. So how also we can understand this relation? Let's take L plus 1 loop integrand of logarithm of Wilson loop. So we can construct the integrand of logarithm of Wilson loop having at our disposal integrands of Wilson loop. So this integrand of log of Wilson loop, it contains L plus 1 loop integrations. If we do all but 1 integrations, we get f. And if we, so in other words, we freeze one of the integration in L plus 1 loop integrand and do remaining L integrations, then we obtain f. And if we try to implement the remaining integration, we find divergence. So we can see that this f it's very closely related to log of Wilson loop, but it's finite. So let me summarize. So we consider this vacuum expectation value of Wilson loop, ratio of two correlation functions with Wilson loops, and also correlation function of Wilson loop and several Lagrangians evaluated at the lowest perturbative level. This observable vacuum expectation of Wilson loop, it's complicated, but it's very interesting. On the other hand, this one, Wilson loop with many Lagrangians, it has nice properties. Its dual conformal symmetry is exact. It's a rational function, but it's simple. It's quite simple. If we want to go to high loop order, we just need to insert more and more Lagrangians, and what we get, we obtain just rational function which depends on more and more variables, and it's not so interesting. But this f, it shares, it has nice properties of these two objects. It's simultaneously non-trivial, and well, and its symmetries are not spoiled, and it is finite. So it's exactly dual conformal, it's a finite observable, and also it's a transcendental function, which makes this one very interesting. And also by counting number of independent variables on which it depends, we see that it depends on more variables than Wilson loop, and by duality than amplitude, amplitude. And as we counted in the beginning, on the same number of variables depend finite parts of QCD amplitudes. And so we'll see that it's indeed very similar to a finite parts of QCD amplitudes. Okay, so let's consider a perturbative expansion of this f. It starts at Born level, and already at Born level it's trivial, it's a rational function, but it could be a quite non-trivial rational function. So how loop corrections, what's the structure of loop corrections? Well, here it's very similar to what we have for amplitude. It's natural to represent it as sum of terms, where each term is a product of so-called leading singularity and a transcendental function. In examples, we'll see how this splitting works in practice, but the main idea here is that a loop correction, it contains a transcendental part, which is described by a number of functions which depends on dimensionless dual conformal cross ratios, and also it contains rational functions, which depends on all these axes. Well, so we can ask questions about these leading singularities, and also a question what is the space of transcendental functions. So it's interesting to study both leading singularities and transcendental functions. Well, in the following, it also will be convenient to us to look in to choose a particular frame. We can send x 0 to infinity, so we cancel out dual conformal weighted point x 0 and send x 0 to infinity. Well, it's just a choice of this of the frame of dual conformal symmetry. So by doing this, we break dual conformal symmetry. But having this function small f, we can always reconstruct capital F. Okay, so why would we do it? If we eliminate x0 in this way, then okay, we have dependence only on x's, and these x's, these are coordinates of a Wilson loop contour, and by duality, it is equivalent as a function of momenta of n like momenta. So this function is a function of in 4 dimensions, and it has the same kinematic dependence as n particle scattering in a massless quantum field theory. For example, n particle scattering in QCD. So in the following, we will look at this function in our words, this ratio of Wilson loop where Lagrangian insertion point x0 is taken to infinity. So let's consider simplest example. Simplest example is a 4-point case, and in this case, with observable been previously studied extensively. In this case, loop correction take this form. So this is a rational function which I call leading singularity, and this one is a transcendental function. So in this case, in 4-particle case, there is only one leading singularity. And functional space, first of all, function which encodes, which describes loop corrections, it's a function of one variable. And well, calculations show that this function is HP is this harmonic polylogarithm function. It's particularly a nice class which extends classical polylogarithms. Okay, so this function was calculated up to free-loop order. So, so at the lowest loop order, it just at Born level it's -1. So at Born level, this observable is just -st, where st is standard Mandelstam variables for particle scattering. At one loop order, it's log squared plus p squared. So as we can see, this splitting with this splitting into transcendental function and the rational function is dictated by transcendentality properties. So first of all, we would like to call this function pure in the sense that it's just a logarithm. It's not decorated with other rational prefactors or algebraic prefactors depending on that. And also a nice feature that here we don't have mixture of different transcendentalities. So we take sum of pi squared and log squared, but we don't have a term which is proportional to pi. So if we assign transcendentality 1 to logarithm and pi, we see that it's this objective transcendentality too. Okay, so two-loop and free-loop functions, they have more complicated form, and two-loop correction, it also contains Li4 functions, and it's fourth power of log and so on. And free-loop corrections, it's also involve, it cannot be described only in terms of classical polynomials. More general HPL functions are needed. Also, this function is known in strong coupling, it's leading term, in strong coupling, and also recently it certain part of for loop result is known. There is a geometric expansion, so-called loops of loops, and in this expansion, a certain three part was studied, and these three part, it in fact it involves contribution from all loops, so it captures contributions from all loops. Okay, so what we're going to study, we would like to study this object beyond 4 points, and we will see that it has a very nice structure. So, well, by doing explicit calculations, we find that in the 5-particle case there are 6 leading singularities. Well, at least we have perturbative data up to 2-loop order. So, so this expression is a conjecture which is confirmed by explicit 2-loop calculation. So here we have 6 leading singularities. It's convenient to represent it in this way, where one of the leading singularities is a Born level 5-particle observable. It means that if we take L0 here, there is only contribution from here, and this function is 1, and these functions are zeros. Okay, but starting from one loop order, all our singularities, all our leading singularities appear, these are, and also they are decorated by certain transcendental functions. So in this 5-particle case, kinematics, there are four-dimensional variables which describe kinematics. So these functions G, these functions describing loop corrections, they are non-trivial, very non-trivial transcendental functions of 4 variables. And we'll see this class of function is particularly well studied. They're so-called pentagon functions. And so this kinematics is exactly kinematics of 5-particle scattering in a massless QCD. And also a new feature as compared to 4-particle case is non-trivial chirality properties. If we have at our disposal 5 momentum, this 5 momentum conservation, then we can construct parity order Lorentz invariant. and it appears in this function as well as in leading singularities. Okay, so let's describe in more details leading singularities. So in order to do it, we'll need to introduce some extra notations, namely spinor helicity variables. So we have a number of momenta, that is d squared is 0. It means that if we write this Lorentz vector using dotted Lorentz indices, it factorizes in a chiral and anti-chiral spinor. And we also need annotations for products of chiral spinors and anti-chiral spinors. Well, in these notations, we find that leading singularities, they take a very simple form. Namely, they are as follows. After I normalize them with a certain prefactor called Parquet-Taylor prefactor. Well, this Parquet-Taylor prefactor is also expressible in terms of these products of spinors. Okay, so why these expressions are nice? Well, we notice that they invariant under conformal transformations. So this conformal symmetry is different from dual conformal symmetry, which we discussed previously. So this conformal symmetry acts on momentum variables. And conformal Bose generators of this symmetry, for example, they take this form its second order derivative in helicity spinors. Well, if you wish, it can be also written as a second order differential operator in momentum, but it takes a particularly nice form in spinor helicity variables. So acting by this conformal Bose generator on these singularities, well, we see that they vanish, and the action of this conformal boost, it's immediate to see. For example, let's consider this one. It depends, point 3 here appears only as an anti-chiral spinor, but it never appears as a chiral spinor. The same for any point 1, 2, 4, 5. It means that each acting by this generator, each term acts trivially, because each term in this differential operator differentiates simultaneously chiral and anti-chiral point, but chiral and anti-chiral point doesn't appear simultaneously. So, and this symmetry is absolutely unexpected. So we cannot explain it by dual conformal symmetry of a Wilson loop. So it's this symmetry, conformal symmetry, is a hidden symmetry. Okay, so what about loop corrections? As I said, the perturbative expansion at a loop has this form. We already discussed leading singularities. They are just rational functions, spinor helicity variables with non-trivial chirality properties. So what about these functions G? How to describe them? So these are transcendental functions of for variables, and they are so-called pentagon functions. These functions have been considered in the context of 2-to-3 production in QCD in other words, for calculation of 5-particle QCD planar QCD amplitudes. Class of function, these pentagon functions, let them denote by P. They have label of weight and another label A. Here it's just enumerates functions of the same weight. They can be defined by the differential equations. So taking a derivative of pentagon function of weight W, we find that it's a sum of several terms. So in differentiating a function of weight W, we find a function of weight W times dialog of a certain function. This functions are called letters, and there are 26 of them. A are just constant. So this class of function is completely characterized by this set of functions W, which are called alphabet. In this case, it's a pentagon alphabet, and this alphabet contains 26 functions, which are called letters. Some of them have quite simple form, just scalar products of momenta. So here by +4, I mean that this one and the plus it's 4 cyclic permutations. And several letters have more complicated form, so they have non-trivial parity properties. So here it's a trace of this with gamma 5 matrix, and here these are the Dirac matrices. So something slightly more complicated than just scalar products. And okay, these functions they are classified up to weight 4. So for example, at weight 0. There is only one function, just constant 1. At weight 1, these functions are just logarithm, and there are 5 logarithms. And at weight 2, they are just the logarithms. There are five functions, and so on. Okay. These functions are algebraically independent. It means that we can write a polynomial of this function, non-trivial polynomial of these functions, which is identically 0. So functions up to weight 2 are known explicitly in terms of classical polylogarism, and starting from weight 3, we can represent them as polylogarithmic iterated integrals. So there are also routines for their numerical evaluation, and so the analytic structure is well understood, and also there are efficient computer tools for calculating them. In particular, they are used in calculation of QCD cross-section for 2-to-3 productions, and also they allow for certain non-planar extension. But now here we only need the planar version. Okay, so using this function, we can write loop corrections here. So for such that a loop correction is given by pentagon functions of weight 2L, and we checked this explicitly by explicit derivative calculation up to L equal to up to 2 loop order. Okay, so this 5-particle observable, this ratio of Wilson loop has very nice limits. So we can take limits are non-trivial. So we can take a soft limit and we can take a linear limit. And in both ways limit, we get something non-trivial. By taking one of the momenta to 0, soft limit, we from 4-particle observable, we get from 5-particle observable, we get 4-particle observable, and similar by taking a linear limit. And this limit is smooth. So usually when we take such a limit for amplitude, we have a non-trivial soft factor, split factor, and it's singular and so on. But here just it's smooth, and it's well, and it's also for us, it's very non-trivial check for all our calculations, because as I said, this 5-particle observable is given by these pentagon functions, which are very non-trivial transcendental functions, which depends on four variables. But by taking this limit, we should reproduce known functions of one variable. Okay, another particularly nice property which we observe for 5-particle F is related to its sign properties. Well, it is known. It is known that the integrands of amplitudes, they allow for now a nice interpretation as a volume as volume forms, and there is an amplitude hidden program to define the amplitude integrands in connection to positive geometry. Okay, but this applies to integrands of amplitudes n equal 4. What we consider now, it's already integrated quantities. So the question is, what does it have a nice positivity or negativity properties? Well, it was observed that it is indeed the case in the case of four-particle observable. But this four-particle observable is just well, at each loop order, it's just a function of one variable, and we find that these definite sign properties, they hold in the five-particle case as well, but now they are much more non-trivial. So, namely, the statement is that these five-particle observable at loop order L, it takes positive or negative sign in the region which is defined by these kinematical constraints, so-called one loop amplitude hidden region. But I don't know. I'm not going to define exactly how this amplitude region is defined. Well, for us, this relation breaks down to this. So well, I hope I defined on previous slide. So S with two indices ij just means py plus pj squared, just Mandelstam invariant. So here all adjacent Mandelstam invariants are negative. So so S12, S23, S34, 45, 15, they are negative. So it's so-called the Euclidean region. So it's not a physical scattering region for amplitude, but it's what's called Euclidean region. And another constraint coming from one loop amplitude hidden region is that this parity order Lorentz invariant, it takes positive. Also, please note that here we have so this is well, so if a momenta were real, this would be pure imaginary, but this is real and it is positive. It's well, another way to understand why we are working in not in the physical region. So momenta are such that these components of momenta can take complex values, but all these all scalar products are real valued. Okay, so in this region, this observable has a definite sign for the whole region. So in particular, Born level observable L equals 0, it's negative, one loop observable is positive, and the two loop observable is negative, and we expect that this pattern holds at higher loop orders. And as compared to four-particle case, it's very non-trivial because this five-particle observable, it's a sum of 6 terms, and we observe just by taking by testing these for thousands of points, random points in amplitude hidden region, that these terms, they can take opposite signs. So so this definite sign is achieved in a very non-trivial way, where individual terms can give contributions of opposite signs, but nevertheless, the result, their sum is of constant sign for the whole amplitude hidden region. Okay, how much time do I have?
So it's like 2 or 3 minutes till the end of the seminar,
okay.
but some extra time, like
okay, well, okay, one then last topic. It's well, about connection to amplitudes. So as I announced in the beginning, we introduced we discussed this ratio of correlation functions of Wilson loop because it very similar. Its structure is very similar to amplitudes, to QCD amplitudes, or non-supersymmetric amplitudes. But question is, okay, is it can be matched exactly to an amplitude? So vacuum expectation value of Wilson loop is dual to MHV amplitude in n equal 4 superpower mills. So now we consider this ratio of correlation functions of Wilson loop in n equal 4, and you'll see that it matches to scattering amplitude in null theory in pure Young mills, and this amplitude is all plus amplitude, all plus helicity configuration. So, okay, these are all plus amplitude in pure Young mills theory. These are a special class of amplitude. They have very peculiar properties. So, as previously, we use color decomposition, and in the following, we look on this color street part of the amplitude in the planar approximation. So, these all plus amplitudes in pure angles, they vanish at the tree level. And so first trivial approximation is one loop, and in one loop they are finite rational functions. So usually QCD amplitude at one loop they are the logarithm product of logarithm, but this one is a rational function. Well, similarly, a two loop order, two loop amplitude is looks like a typical one loop QCD amplitude. In other words, there is a shift in transcendentality of these all plus amplitudes as compared to more generic amplitudes in Young mills in our helicity configuration or in QCD. So like for amplitudes in n equal 4, we can factor out infrared divergences in form of infrared poles and consider finite part of all plus Young mills amplitude. Okay, so this amplitude has been calculated up to 3-loop order in the 4-particle case and up to 2-loop order in n-particle case. And the calculation of this amplitude is quite, it's a hard task despite of this shift in transcendentality. Well, it's a hard calculation by Feynman diagrams, and that's why it's not like for n equal 4, it's not 5, 6, 7 loops. It's here perturbative data available at a much lower loop level. Okay, we observe a nice duality between this all plus amplitude and the observable, which we discussed previously. This correlation function of Wilson loop with Lagrangian insertion. At the lowest perturbative level, this duality looks as follows. So here we have one loop all plus amplitude, and here this bottom level and particle observable normalized with endpoint Parquet-Taylor prefactor. This prefactor we needed to balance helicity ways on both sides of this equation. By the way, as I said, this function is invariant on the conformal transformation, so it's also a property of this one loop amplitude, one loop all plus amplitude. It's this rational function is conformal invariant. So that's why it was for us natural to expect that they could coincide, and it's indeed the case. What is more interesting that this duality also holds at loop level. So it looks like this. So here we compare finite quantities in 4 dimensions. Here we have a finite part of all plus amplitude. Here this our observable, this ratio of Wilson loop, logarithm of it, and here this is a finite part of MHV amplitude, or if you want, finite part of vacuum expectation value of Wilson loop. At 4 and 5 points, this one is known at any loop order, and also for 6 points, it is also known for quite high loop order. Well, we find a nice agreement of this equation with available perturbative data. So we know this one at 2 loop order in 5-particle case, for example. Okay, so and these this data, this allows us to make predictions for all plus amplitude. Also, I should mention here that we cannot reproduce full amplitude. Its duality works at the level of highest transcendentality. So we keep so from the amplitude, from all plus amplitude, we can predict only the maximal transcendentality pieces. So in this way, this relation gives a new result for, namely, a free loop 5 particle all plus amplitude and for loop 4 particle all plus amplitude. Okay, well, let me just jump to conclusions. So we considered a nice finite observable in an equal mills, which resembles a lot scattering amplitudes in QCD, scattering amplitudes in QCD or in non-supersymmetric gauge theories. And this observable has very nice properties. It has a very non-trivial positivity properties. It has hidden symmetries, in particular conformal symmetry of its hidden singularities, and it reproduces maximal transcendentality part of all plus amplitudes and pure mills. Well, thank you. I'll stop here.
Thank you. Are there any questions?
I think you never mentioned planar limit, right?
No, planar limit is very important. Yes, for us. Yeah, I tried to put it on all slides. No, it was planar amplitude. Yeah, of course. Planar limit is very important for us.
Yeah, because this dual conformal symmetry is. I think
yes,
it's important. Yeah. Okay, sorry. Yeah.
Well, as a motivation, I started from the fact that amplitudes, MHV amplitudes in n equal 4, they become non-trivial only starting from 6 points, because for the 5 particle case, BDS ansatz expression is exactly the null order, but okay, it's true only in the planar limit. Non-planar amplitudes in n equal 4, they are already non-trivial in 4-point case. In 5-particle case, they're very non-trivial, and they are very similar to non-planar QCD amplitude of the same loop order and the same number of particles. So this motivation works if we want to consider an observable which is planar. And which is similar to planar QCD amplitudes of the same loop order and the same number of particles.
Other questions? Can you repeat? So this you have this conjecture about duality of two quantities, right? But is it based on examples, or it's?
Yes, it is based on examples. Well, in particular, we can see it at Born level. Okay, so okay, so which perturbative data we have at our disposal? For all plus amplitude, we have 1 loop n particle amplitude, 2 loop 5 particle amplitude. Okay, 2 loop n particle amplitude. Let's see, 2 loop n particle amplitude, and 3 loop 4 particle amplitude. Beyond this one, we don't know all plus amplitude in pure mills. These are, well, these amplitudes, it's hard to calculate them. They are calculated by Feynman graphs, and in order to do it, we need to go through standard procedure for calculation of QCD amplitudes. It means we draw all Feynman diagrams, we reduce them to master integrals, then we try to evaluate these master integrals using differential equation, and it's well, it's a difficult exercise to do it, and so far it's known only in the 4 particle case at 3 loop order, also in the non-planar case, but beyond that it's difficult. So for example, calculating in 5 particle case 3 loop, it's well, it cannot be done. Well, it will not be done soon. It won't be done soon, because we would need to know 3 loop 5 particle. We must take all master integrals, so it's difficult. So this conjecture, well, it's difficult to check it using at high loop orders using perturbative data. Well, so yes, this is based on examples, but we have agreement with all available data.
Well, but like this other quantity, which is not MHV, so this Wilson loop computation, is it available for all those examples that were in the previous slide?
Yes, yes, even more. So
even more.
Is observable. We have for example, what I said, we calculated this observable F ratio of Wilson loop, which we calculated two loop order, and this two loop order gives prediction for free loop all plus, this free loop 5 particle all plus. This is because of this shift of perturbative order, because because this all plus L loop, it is like L plus one loop standard QCD amplitude.
Mm-hmm. And it's simple because, like, to what extent it's just based on the self-dual part of Young-Mills? It does have some like vertices from a complete Young-Mills, right? So as far as I know, like, it simplifies because only
well, at T level, yes, it can be explained by also by this vanishing can be explained also by supersymmetry, but at one loop calculations, it's more. There are some divergences. So this non-trivial, this rational function, it's subtle. It's quite subtle. So we need to construct integrand in the dimension. It contains so-called mu terms, and they give a non-trivial result. Probably I should mention that there is also duality between all plus amplitudes and MHV amplitudes and n equal 4, but at the level of integrands. It's works of Vern, Dixon, Kosover from 2000, something like this. There they give a procedure of how to obtain integrand of all plus amplitude from integrand of MHV in n equal 4. So there's a prescription how to insert mu terms, and this duality was checked at one loop, and then by other people extended to two loop integrands, but d-dimensional integrands.
Mm-hmm.
So something similar has been known previously, but our statement is already for integrated quantities, not for integrands.
Okay, thank you. Other questions? Okay, I also want to ask one like general thing. So you started by saying that well, you want to compute loops because you want to like sum up this series. But like, I'm not expert in this, but people say that the coupling constant is large, so this series diverges. So what is the relevance of like this expansion?
Well, as I said, motivation here is to be able to calculate loop corrections for amplitudes, and if we are thinking about QCD amplitudes, it's exactly what is needed for phenomenology. So in QCD, if we consider scattering at high energies, then we just need to know several corrections. One loop corrections, which corresponds to next to leading order, is not usually already not sufficient, and we would need next to leading order. It is like two loop. Well, usually it is two loop amplitudes in QCD, and maybe for some process it is required next to next to the node that is free loop QCD amplitude. But perhaps more than that, for QCD we will not need it. But calculation of QCD amplitude is hard, so we want to learn new techniques how to do loop calculations efficiently, and N equal 4 is a nice testing laboratory. For example, these QCD amplitudes, they have mixture of different transcendentalities, but observables and in equal 4, they have uniform transcendentality properties, which makes them simpler, but at the same time, they resembles a lot QCD amplitudes. So if we learn something about these amplitudes in N equal 4, or observables N equal 4, amplitude like observables like one I discussed today, maybe we will learn something about QCD amplitudes.
So eventually you are saying that it can be actually checked, this expansion in like actual experiments.
So for QCD, yeah, it's what required. We need to know, we need to know loop corrections for QCD amplitudes, and for example, two loop amplitudes. So then using them, we can calculate cross section, and when we compare with cross sections measured in experiments. But of course, it's a huge machinery. It's just this final part of amplitude. It's just a small piece, which is indispensable for calculation of cross section. But of course, there are a lot of other technical difficulties which are needed. But it's what required to draw these graphs like this. We certainly need to know amplitudes.
Okay, thank you. So last call for questions. Okay, since there are no other questions, thank you very much for a nice talk.
Thank you.
And thank you everyone for coming.